大家午安，刚好清醒。接下来这一场是由 Justin 带来的，怎么用 Rust 做高效的 Webassembly 的网络应用。
大家好. I'm going to use English for this, if that's okay. Thanks everyone for coming. My name is Justin, and I'm going to talk to you about how to build fast web apps with Rust, Wasm, and U. First, a little bit about me. I usually live in Toronto, but it's really cold in the winter, so I came to Taiwan for the winter to escape the cold. But then, due to COVID-19, decided to stay here because it's a little safer. So that's why I'm here in Taipei right now. But honestly, I'm really happy to be here, despite the really hot summers. So the agenda for today, we'll be talking about how to write fast web applications. I'm going to be focusing on the U framework. So what is U? It's a framework kind of like React.js, if you've heard of that. But it's written in Rust, and it targets WebAssembly. And so we're going to be talking about those two. We'll start off by talking about some background information that you'll need to know to kind of understand the talk. And then we'll dive into my recent adventure to improve performance benchmarks for the U framework. And I hope you find it interesting. Along the way, you'll learn how to better improve the performance of your own applications, as well as how UI web frameworks kind of work behind the scenes and the tricks they use. Oops. And just before we kind of jump in, I just want to say that I come from like a web developer background. And so a lot of the points I'm going to be making kind of like compare this like Rust, Wasm world with JavaScript and the differences. So first, a little bit about Rust. This is the Rust track. Some things I think are awesome about Rust is Rust is a statically typed language, so it'll help prevent you from making these mistakes where you use like a string instead of an array somewhere and you don't understand why it's not working. You won't have to worry about that with Rust. If you're writing web applications in JavaScript, it's kind of like writing it in TypeScript, right? Second, there's this concept of zero-cost abstractions with Rust. So that means when you are writing your application, you have to think about, oh, how can I write this the fastest, most optimal way? Behind the scene, when the Rust compiles your application, it doesn't matter if you're using an iterator or a for loop or something, it'll compile to the same optimized code. So that's what it means when we talk about zero-cost abstractions. And then lastly, Rust is a manually managed, uses manual memory management. And so you don't have to worry about a garbage collector running in the runtime. So a lot of languages like Golang, for instance, like it uses a garbage collector to efficiently manage memory, but that means that it'll interrupt your program to free up memory or like move stuff around, and it kind of makes it so your performance isn't as predictable. It doesn't necessarily mean that Rust is faster for not having a garbage collector in some cases, but it is more predictable. So now we're going to talk about WebAssembly. This is really a key part. WebAssembly is supported in all major browsers now for a few years now. And so while frameworks like U and other WebAssembly frameworks haven't caught on like super mainstream yet, it's kind of around the corner. So WebAssembly, what is it? It's a programming language. It's a programming language written in like, it has like a binary format, which is really super compact. It kind of looks like machine code that you couldn't really understand. Like, it looks like that. But you don't have to worry about that because the whole point of it is that it's kind of an intermediate representation. So you write code in a high-level language like Rust, and you compile it down into WebAssembly, and it's just this format that can kind of run in many different places. So all browsers can understand it. You don't have to actually understand how the WebAssembly is written. It'll just be that way. another thing that's nice about WebAssembly is there's no garbage collection happening that would be happening with JavaScript. So the performance of a WebAssembly application is, again, more predictable, just like I was saying about Rust. And another thing that's more predictable about it, this is a nice diagram from Lynn Clark. Basically, when a browser goes to run JavaScript, it's going to parse out all the code that you wrote and create this like abstract syntax tree and try to understand what your code is doing. And then it's going to compile and optimize it, and then it's going to re-optimize it because JavaScript might be slow. It's going to find the parts of your app that need to run really frequently, so it'll make those really fast. So there's all this overhead, and then you also have the garbage collector. With WebAssembly, it's already in a super readable format, so it just needs to decode the instructions and then compile, optimize, and then execute. So you can see it's a lot more like streamlined. It's not necessarily to scale. JavaScript is still really fast, but it's a little bit simpler in WebAssembly. Yeah, so another thing that I want to say is that WebAssembly is not necessarily a full-on replacement for JavaScript. It actually just works really well with JavaScript. When you're creating WebAssembly, you can actually create a WebAssembly module with JavaScript, set it up all in JavaScript, when you create the WebAssembly module, you send this list of functions that WebAssembly can use to call into JavaScript, and you send in a list of functions that WebAssembly can call out to JavaScript. So it kind of works both ways, and it works really nicely. But one thing to keep in mind, despite how fast and cool WebAssembly seems, there's still a bit of overheads involved with using WebAssembly. So WebAssembly has its own memory separate from JavaScript. And so if you're calling from WebAssembly to say a DOM API, like I want to create an element in my web page and display that, and you want to put some text in there, hello world. Now that hello world text will start off in WebAssembly. You're going to call out to JavaScript. JavaScript's going to copy that memory from WebAssembly and allocate it in JavaScript land. And so you're kind of paying the cost twice whenever you're passing strings across. And there's other quirks like this that you have to be aware of. More so like web framework developers have to worry about. And now we come to U. One sec. U is written in Rust, compiles WebAssembly. So these benefits of nice things about Rust and WebAssembly, we get those all for free. So we're kind of building on the shoulder of giants here. And so what do you get with U? Well, you get nice efficient rendering. U uses a virtual DOM. And what that means is it's going to keep a copy of what is currently displayed on the screen. And when your app updates to a new view, say a counter updated, you will keep track of, hey, what was previously on the screen and what do I want to be on the screen? And it'll find the minimum difference, say, oh, everything's the same except for that one piece of information, and it'll make that change. So it's quite efficient that way. It also makes it really easy to do kind of intense processes in the background. So on browsers, you have web workers, so U makes it very easy to send these tasks to the background. And here's a little view of what some U code looks like. It looks just like HTML, really, but inside you're using Rust expressions. And so if I have an app and I want to say, hey, I want to display a user, their first name and last name, U uses what's called a procedural macro. Oh, that might be better, actually. You can leave it off. So this view is displaying a user, and then when your component updates, like the first or last name, you will make sure to keep those in sync. And yeah, explain the virtual DOM and then the diffing algorithm. So here's a little illustration of the diffing algorithm. I know it's a little hard to see, but imagine you have like the layout of your app, in a tree. So you have like a root div component and a list over here, and then another element with some text saying it's downloading. When let's say that thing finished downloading, and you want to add a new element to the list, and you want to add an image, everything's going to stay the same except for the things that are different. So you won't touch these list elements. It's not going to re-add those to the DOM. It's going to say, hey, I know that you want to just add another element here, so it's smart enough to figure that out. Okay. And then here's another like kind of mental model you can use to understand how this is all working out. So here we have everything that's living in WebAssembly land, and then this is all the JavaScript land, okay? So here we have your U application, and it's written in Rust. And then what we do is we build on these two libraries, WebSys and JSSys, and what these are bindings to DOM APIs, JavaScript APIs. So for instance, if my application in Rust wants to call console.log, okay, I'm going to go through the WebSys crate, which has a console_log function that directly maps to the JavaScript. So that's all in Rust, and it makes it really easy to do everything you want to do in Rust, and you get all the type checking guarantees and manual memory management benefits while staying inside Rust. And then there's this glue underneath, Wasm bindgen, which creates Rust generated Rust code as well as generated JavaScript code, which makes it really easy to cross this boundary. Like I was saying, like if you want to pass a string across, there's a lot of stuff you need to do. And so this will take care of all that for you, so you don't have to worry about it. Okay. So now we're going to get into the meat of the talk. This adventure to defeat the performance benchmarks, okay? So what do we care about from benchmarks? Well, we want our apps to be fast, right? And so you might think, okay, so we're building on Rust, WebAssembly, and U is pretty fast too, so it must be pretty good. And so what happened is there's this popular open source benchmark suite on GitHub, open source. Stefan Krauss created it, and it's like a simple app that a bunch of frameworks will add an implementation to, okay? And then they all do the same exact behavior, and then they'll measure it over like 10 different times to see which ones behave the best, right? It measures how fast your framework renders the app, how much memory it uses, and the startup time. And we're going to be focusing on the rendering speed. Okay. And since every framework needs its own implementation, you'll see that the implementations actually vary quite a bit. Okay. So there's a lot of freedom, but it also might be a little bit unfair. You know? So when we look at like a React framework implementation versus the Angular, they might use different tricks to try to make theirs seem faster. So we have to keep that in mind. And here's what the framework or the benchmark looks like. So this is the U1. We put the name of U on the top, and we have this jumbotron, which has a bunch of controls. Okay, so it's supposed to model like a real app. So like you'll create a list of data. You want to append some rows. You want to update every other one. Maybe you're displaying a list of data and you're filtering it out. It's just like a very common thing that you would see on a website. And so that's the basis of it. Okay. So it says JavaScript Framework Benchmark, but there's a lot of WebAssembly ones too. So maybe we should change that name to JavaScript and Wasm Framework Benchmark, but that's okay. But we're going to talk about how U stacks up. So I don't know how you guys feel knowing all the stuff that I just told you about Rust and WebAssembly and U. Should be pretty fast, right? So out of 150 frameworks, how do you think U stacked up against the rest? Any guesses? Any guess? 100 out of 150? Number one. No, it wasn't number one. Let's say like middle of the pack or at least top 50 or something, right? Yeah. Ooh. Yeah, I mean, embarrassing, I think, right? Like 149 out of 150. And you might be curious what the 150th one is. Well, there's this other WebAssembly framework, and it was written by Microsoft. It's called Blazor, and it's written in C#, and it has this big runtime, so it's a lot slower. So I don't really necessarily feel good about beating that one. I'd like to do a lot better. I want to have people say, hey, JavaScript, maybe we can do better. Maybe we can make things faster. We don't want to be coming in last place. It kind of reminds me when I was in high school, I would do a lot of running races, and I would come in last place, and it really sucked. So it really motivated me to like try harder. So here's a little like, here's what the benchmarks look like when it spits out all the data. On the left, green is good. On the right, red is bad. And it's kind of, I don't think you'll be able to see it, but this one right here is you, and this is Blazor. It's really bad. So we got to fix that. So how are we going to make this fast? Does anyone have any guesses, by the way, like why this ended up so bad? Here? Yeah, maybe the diffing algorithm is not that great after all. I told you that it's going to make the minimum number of changes, but maybe I lied. You don't know because it is open source. You could check, but any other guesses? What's that? Yeah, maybe overhead from WebAssembly. Yep, yeah, that's a good idea too. Any other guesses before? The answer is there's a lot of reasons, but we'll go through a bunch. Some other reasons is because there's that overhead. There definitely is some overhead, so no doubt about that. Maybe it's because maybe we're calling across that boundary from WebAssembly to JavaScript too often. That could be a reason. Whenever we need to copy a string out, because we're displaying a lot of text, especially in this example, all of those rows have text. So copying out each string and allocating it in JavaScript, that could be pretty slow. Yeah, maybe on the use side, maybe the implementation just isn't that great. Maybe the diffing algorithm could use some work. So we're going to talk about a couple different experiments, 3 experiments that I did over the past like month or 2 when I had the time, and try to figure out what's going on. So first, the first experiment is very much what this gentleman was saying. Probably there's a lot of overhead, so maybe we don't have control over that overhead, but we can minimize the number of times we jump across from WebAssembly to JavaScript to call these APIs. So if we can cut down the number of DOM API calls, maybe it'll be faster. Okay. So we were actually in the middle of rewriting the diffing algorithm like about two months ago for you. And we noticed that there were some opportunities to maybe cut down. So I'll give an example. Well, first I'll explain kind of the DOM API calls we have to work with. So imagine you have an app that wants to display a list of data. For each element or for each item in that list, you have to create a new DOM element. So that's like a div or a span, these types, okay? And then for each of those, you have to add an attribute, maybe a class name, add an event listener, so when you click it, something happens. We need next sibling and insert before. This is when we're trying to update an existing row, say we change the text, for example. We have to delete that node and then insert it again with a new one. Okay, so that's what these calls are for. So we have to kind of find where to insert that node. And so we're going to focus on those 2 actually. So next sibling and insert before. This is what's called like a hot path. Like we call these functions for every single diff that we do. It happens a lot of times. So the idea is that we could cut this in half, and we should see some savings. Okay. So we notice that we're always tracking the node before where we want to insert the next node. Okay. But you'll notice there's only an insert before. There's no insert after call. Okay, so every time we're saying, get the next sibling and then insert it before. Okay, so that's an extra call that maybe we don't need. So we refactored it. Here's like a little drawing I did. Okay, so get the next sibling and then insert before. All we want to do is put something after. And so we changed it so that instead of holding on to this, keeping track of this node, we keep track of this one. So we just need to do the insert before. Okay. So let's see how that did. So this is before and after, and it's pretty hard to read. I kind of expected that, but luckily the colors kind of help. The colors are basically the same. It didn't really help that much, unfortunately. That's not to say that there isn't improvements to be made for optimizing these calls, but it definitely isn't the main thing that's slowing things down. So in all, like, it's hard to see, but we actually got about 10% speed improvement on that change, which is pretty good. Like, if you do that enough times, 10%, 10%, 10%, it'll build up. But we need something a lot bigger. Yeah, so what actually improved was when you're updating rows, it got a lot faster, which made sense because we were cutting down those DOM API calls. Okay. So the next experiment, we're going to look into the implementation. So I mentioned that in this benchmark, every framework has to create that app. They have to create that app that's, okay, click a button, create a bunch of rows. It's a very, very simple app. Someone created that implementation about a year ago. And so the way they implemented it is, yeah, very simple. They have a single component that just says, this is all the data that I want to show, and then it responds to a click event, and it'll say, okay, I have all this 1,000 rows in my state. I want to add another 1,000 rows, or I want to switch these two, and then when it updates, it re-renders everything. So I think we got to fix that, okay? And just a little highlight of Vue components. And this is something that could be really relevant to your own apps. And it applies to not just Vue, but also React and other frameworks too. So when you have a component, you handle its own state. So in this case, we have an app that has, let's say, 1,000 rows of names like that it keeps track of internally. And then whenever you click or interact with that app, the component can decide, did anything change that I want to display? Maybe nothing, maybe I don't need to share that particular update. It can decide that. It decides what it wants to show. And there's some other properties that are useful for when you're combining components, which we'll definitely want to do. So you can use components inside other components. You have this whole nested tree. And then each nested component can get information from the parent. So how would we split this up? Well, we definitely don't need to ever change this part up here. It's always going to be the same 6 buttons. So let's just put that in its own component. So we don't have to worry about comparing, did this create 1,000 rows button change since the last time it got clicked? Yeah, obviously not. Okay. And then another thing we're going to do is we're going to say for each of these rows, we'll make them a component as well. And so when you're swapping 2 different rows, right, all you need to do is check those 2 rows if the information changed. The rest of the rows, so a pretty yellow car here, if it didn't get changed, we're not going to bother checking to see if each of its elements had any difference. So we're going to save a lot on that. Okay? So just to review, we have a new Jumbotron component, and we have a bunch of new row components. Okay? And let's see that. Okay. Quite a bit better, actually, right? We went from a lot of red to a lot of like yellow and orange, right? So kind of as expected, whenever you're updating this row right here, is whenever you're updating every 10th row, that's the benchmark. And so we improved a lot. We went from, we cut down the time by 60%. That's huge. And this other one, when we're swapping 2 different rows, or actually when you select a row, it gets highlighted and you have to display it differently. It cut down by like, I don't know, 95% or something. So obviously we just needed to improve the implementation, right? Well, unfortunately this revealed another problem. This This benchmark, unfortunately, got a lot worse. And what this is when you're creating many rows, creating 10,000 rows specifically, okay? So what happened was we switched to using a component for row, okay? And it seems like there's some extra overhead that U is adding that could be a lot more efficient. That's the conclusion that I come to when I see it got 3 times slower. There must be some stuff that we're doing that we shouldn't be doing. Okay. So now we go to Chrome DevTools to understand what's going on. I will say that I looked at the implementation for components, and it seemed pretty okay. It seemed fine to me. I'm pretty familiar with the code. And so I had to try to understand what was going on using tooling that's available. So this is just Google Chrome. You can record a session for performance. And I just clicked the create 10,000 rows button, recorded it for like 10 seconds, because that's how long it takes. And this is what we get. And now, so there's 3 lines here, and they're mapping 3 different things. So we're mapping how much memory is used over time, how many nodes are created in the DOM, and how many listeners are added to the DOM as well. And so it's a little hard to see, but we go from basically, so we go from 63 nodes before the click to 110,000. Okay, it's a lot. That means that every row probably has 11 nodes, so 10,000 rows, right? And then listeners, we go from 41 to 20,000. So it seems like every row has 2 listeners. Okay, it's important to know for later. But they all kind of follow this very smooth line, right? It's like, you can't really tell, but it's like this little, it's just like steps, but it's like really, really fine grained. So the browser in a very smooth fashion is creating all of these nodes, okay? And then we get to this part, which is really important. We have this purple region. Does anyone know what the purple region is? Yeah, so it's when the browser is laying out the screen. So after your app finishes running JavaScript or WebAssembly, it's consuming all the resources. So now once it's done, it gives it back to the browser to say, okay, I've told you everything that I want to display. Now display it. And so it takes about a second and a half for the browser to take all of those rows that you've created and put them onto the screen, measure, how, the individual size of each of the rows and all of that. So it takes a little bit of time. Anyway, so when you guys look at this, do you get any ideas of what might be happening? It took me a while, but curious if anyone knows. It's a really smooth line. Well, it turns out smooth is bad. Smooth is really bad because what that means is the browser is creating these DOM nodes in kind of real time with your app. And what I researched a bit, and it turns out it should be kind of like jagged. It should be like flat, and then a big jump, and then flat, big jump, like that. And what that means is you say you create 1,000 nodes in the DOM, and then what should happen is the browser collects all of those for a short amount of time, and then creates them all at once. And the browser does it, sorry? Yeah, exactly. It should be a batch update. But apparently, the batching is not happening. So why is the batching not happening? Any ideas? It's not something we have direct control over. Yeah, it could be memory allocation. I think there's definitely overhead in that. Yeah, I mean, so really actually maybe that is like kind of the source of it, but essentially what I've deduced is that because when it's rendering, it's taking each component at a time and allocating for each row, it's going to allocate the virtual DOM representation for each row item. And so yeah, there's allocation overhead for that within WebAssembly. But then it seems like there's too much time in between each row that the browser is saying, hey, I'm not even going to batch this. We already passed this like timeout. You didn't call the next create node in time. So I'm just going to go create it now. I'm not waiting. The batch is done. So the batches are really, really short and small. Yeah, so what we're looking at now is trying to improve component rendering within U. And we're specifically trying to create 10,000 rows as quickly as we can, okay? And so I drew up a little hand-drawn diagram, and this is what's happening behind the scenes within U. And what we have is, on the left, this is supposed to represent the U scheduler within the rendering process, okay? So what the scheduler is going to do is for each component, we're going to create a task. It's like a unit of work that the scheduler is going to prioritize in order, okay? And it's all single-threaded. So we decide the order in which we want to do all these operations. So this is a queue. So the top is like a destroy queue. All the destroy tasks go in there. Then we have a create queue. This is for components. So whenever you're destroying a component, we prioritize that first because we don't care if anything happens to the component after we know it should be destroyed. So let's just destroy it right away. And then create is batched together. And then we have update queue. And now the update queue is where things are definitely not as efficient as they could be. Because inside each update task for a component, we're doing too many things. This is what I ended up figuring out. So we're first going to say, OK, swap 2 rows. So the row component should update, right? So we update the information. And then once we update, we allocate the virtual DOM representation of that row. And then we'll compare that virtual DOM representation with what is currently on the screen. And then finally, we'll render all of that to the screen. So we're doing too much stuff all together. We're doing allocation. We're doing a lot of processing to figure out what the actual difference is, and so on. So what we did is we split the update queue into 2 separate queues. So we have an update queue and a render queue now. And I think it makes a lot more sense, right? So the update queue will handle the allocation. It'll decide whether or not you want to update your component, and we'll put those tasks here. And once all of those have been processed for all components, then we'll start rendering all the components. So it's kind of a phased scheduling system. So we do all this work up front, and then we try to batch all the DOM API calls as closely together as possible so that the browser can do the optimizations it can. So I think you can understand that. And so here's the difference. So we were specifically focusing on creating many rows. And so it went from, this is like 7 seconds to 2.6 seconds. So we cut it down by like 60%. And we got some savings elsewhere too. It seems like maybe there was other places where that component rendering wasn't as efficient, and it was cropping up when we were updating certain rows, or swaps seemed fine actually, but there's some other things. So reducing that time between creating DOM elements helped our browser optimize it. So if you think about it in terms of your own app, when it's nice when you can like batch all of your changes together versus like spread them out over time. And so here's what the chart looks like after that change. You can see what I was talking about. It's like it's more coarse. It's not as a smooth line. The browser has time, in certain milliseconds to batch together a bunch of calls together. And so this is what it was before. It's totally different and much shorter. But you'll notice this the layout time is the same. We didn't cut any time off that. We just made the scripting portion a lot faster so that the DOM or the browser could properly optimize. So we're getting towards the end. I just want to say that this journey is not over. We're still towards the towards the end of the ranking or the back of the rankings, but definitely not the worst. We're better than like React now, which is great. But there's more stuff that we could do, and I just want to highlight a few that I think are really interesting that I plan to implement into the U framework. So one is reducing add event listener calls. If you remember, we added 2 listeners for each row in our example here. And so if you think about that, it's like 20,000 event listeners. What you can do instead is you can only add one, let's say a click listener. We add one click listener to the whole app, and then behind the scenes, the framework, when it receives a click event from a particular point in your app, it'll figure out where to send that event to, which row to send it to itself. So it's not relying on the browser. And this turns out to be much faster, especially when we're crossing that boundary from WebAssembly into JavaScript. And then a couple other things. We're going to keep looking at improving the render phase efficiency. And there's another thing called, there's an API called clone node. And so what that is say for each row, I noted that there was 11 nodes that make up each row. And those nodes are like, okay, a container node, and then inside there's a text node, and then maybe a delete button, and all these things. Together there's 11. And so when you're creating 10,000, you're creating 10,000 copies, basically, of the same thing. And instead of, for each one, creating 11 nodes, you could just create it once, clone the whole structure 10,000 times. So then you cut your DOM API calls by 1/11. So that's something we want to look into too. And there's just other things that we can do to reduce, to improve performance at compile time, because we use a lot of compile time kind of magic to analyze your app to make it faster. So I think that's pretty exciting too. And then also I think there's a lot of like these 10% improvements that I mentioned at the very beginning that could be figured out by just like looking through the code and finding improvements. And so if any of this sounds interesting to you, please like, reach out and think about contributing. It's a really awesome community, and it's kind of what keeps me going for sure. So thank you everyone for listening. We can do a few questions, and then I have some links as well to the project, some documentation. We have documentation in Chinese, thanks to Chiu. Thank you. And we also have like a chat room that you can continue the conversation about performance if you want. And you can see the benchmark rankings. We're definitely better, but not the best. So any questions? Yeah. The memory footprint of the U app. The memory usage. Yeah, you can analyze that within the Chrome tools. Yeah. Yeah. I see. Yeah, so the question is like latency versus throughput. How do you measure that in performance benchmarks? Yeah, I mean, I think that this particular benchmark that we've been focusing on, it really is about, it is measuring latency, actually. I mean, so each of these benchmarks is like, do a bunch of options and try to return, you're basically blocking the UI thread, so the user can't do anything when you're doing those operations. So you want to return as fast as possible to reduce that kind of latency to have a smooth experience for the user. But there's also, I think, a lot of benefits that you can get from WebAssembly, just like for improving the efficiency of like data processing and stuff. And then that type of work you can always put to the background, and you should see a lot more benefit than if you were just using vanilla JavaScript. Anything else? I think we're out of time. Thank you everyone for coming. I'm going to try to write up a blog post about this soon, and hopefully we can add more interesting benchmark improvements to that. So thank you.